All right, friends. Let's do this. So homework is due. First homework is due tonight, 11 o'clock. Don't forget. I hope you are all signed on. Some people have issues. Particularly people who sign up late for the course in general were not automatically added to the scheduling database, but after some emailing back and forth, most people have gotten on. If you are not on yet, you have to let me know. Okay? So then I can send a final email to Sapling telling them you should be added. All right. So today we're going to talk about accuracy and dimensional analysis. And most of you have already had a good flavor of this because this is one of the topics was reflected in the discussion sections. Okay, so here is a backyard basketball hoop. Here's my friend again and myself. And we hang out every now and then and just play, just going to shoot the hoop. So he's doing pretty well, typically. And after 8 out of 8, pretty good. And here I am. I'm hitting the board first. I have to warm up a little bit. And eventually I get a basket, which is 1 out of 8. So this, the difference between him and me, evidently, is there's an issue with accuracy here. I'm not nearly as accurate as he, which is also explains directly the difference in our salaries. So accuracy is important in the sciences. Okay. There's also another word which is related: precision and accuracy. This is a picture in the book that kind of nicely illustrates the difference between the two. This is a very high precision and high accuracy measurement, if you wish. You see those 5 dots there and up very close to the bullseye, which is very good. High precision and high accuracy. Okay. So this is a high precision, which means precision means the reproducibility is very high. Okay? The repeatability is very high. See, all these guys are very close to one another. But the accuracy is low because they should have gotten here. Okay? And then the last example is low precision and low accuracy, in which case they're both spread out a lot, so the repeatability is low. And the accuracy, where they should end up, is also very bad. Okay? So these concepts play an important role in the natural sciences. Okay? And if you do a measurement, for instance, in your chemistry lab, you may end up in a situation like this. There's a cylinder, and there's little marks here in the cylinder, and you have to read off the correct number. And that is not always easy. Okay? So here's an example. This is 50, 51, 52. And then here I see this line here. Not exactly where it is. Let's say the bottom, I take this bottom, the bottom of this line here. And what is the number here? So I have 1, 2. So 52 is good. I know that. But then the last number I'm not quite sure about. I'm estimating 7. That could be 8. 9. I don't know. So the last one here is definitely subject to error. It's an estimation. And so things like this are very relevant because you have to specify how significant these numbers are. Because if I put in like a 7, 5, 4, 3, 2, 1 behind this, then if I'm going to give you that number without any information, then you may assume that all these numbers are significant. In reality, they're not. Because I cannot be sure what happens after this 52. The 7 is not significant enough. Okay? So this is a recurring theme in scientific measurements where you are not sure what the last number is. And therefore, this number here has only 2 significant figures. Okay? So we have to be able to work with that. So let's look at numbers in general, and let's see what is the significant information in a number. Okay? So significant figure simply means numbers that matter. And we're going to look at numbers and see when they are significant and when they're not. So what counts as a significant figure? If I give you a number, what is the rule of thumb? So you know when I give you a number what I mean by those numbers. Okay? Every non-zero integer counts as a significant figure. Every non-zero integer counts as a significant. So basically everything that you can count, 1, 2, 3, 4, 5, up to whatever, these numbers are all significant if it's an integer. Okay, zeros. Here it gets interesting. Leading zeros do not count as significant figures. So there's like 1, 2, 3, 4 numbers here, and there's only one significant figure. Why is that? Well, look, I can rewrite this number as 2 times 10 to the minus 3. There's only one significant figure. The position of the decimal point is arbitrary. These zeros contain no information. Okay? Captive zeros, zeros sandwiched between two non-zero integers, are significant. So in this particular case, this number here has 1, 2, 3, 4, 5, 6 significant figures. Trailing zeros are significant if they follow after a decimal point. Then they are significant. If they don't, okay, then they're not significant. For instance, these guys are not significant. These guys are behind a decimal point, okay, but there's a number behind it. This is the first non-zero number, then this is a significant number. In this case, these guys are significant because they follow after a non-zero integer. If this would have been a 0, then it would be 0 significant figures. Okay? So they count as a significant figure after the decimal point if there is a non-zero integer to the left of it. Here that's not the case, that's why these are non-significant. Okay, and then finally, exact numbers. For instance, a fraction, 3 over 4. 3 is a significant figure, 4 is 2. These are infinitely precise. 3 over 4 is infinitely precise. That number, that fraction, is an exact number. There's an infinite amount of significant figures. Pi is also a number which has an infinite amount of significant figures, meaning that these numbers will never ever limit the significance of your calculation. Okay, now, once we have numbers and we look at a number and you can tell how many significant figures the number has, what happens when we do a mathematical operation with these numbers? So let's first look at multiplication and division. And this is the rule that we stick to. So the result of this multiplication or division has the same number of significant figures as the least precise measure in the calculation. What does that mean? It is this. I have here two numbers that I multiply. One is 3.56, the other one is 2.0. If you do that on your calculator will say the answer is 7.12. But now you have to check which of those numbers here, these are three numbers, which of them are significant. This rule says the answer has to have the same amount of significant figures as the least precise measurement in the calculation. I have two numbers, they are, let's say, assume they come from measurements. Okay? This is the one that has two significant figures, this one has three. So this one is the least precise, it has two significant figures, which means that this guy also should have two. In other words, the answer here is 7.1. This is very annoying. All right. Not so good. Sorry guys, the computer is completely frozen. Okay, sorry folks, I have no idea what happened. Here it is, froze. It happens. All right, after the short introduction, I'm sure you appreciate the following. So we talked about significant figures, what happens when you do a mathematical operation, and distinguish multiplication and division from addition and subtraction. There's two different rules, they're different. Okay, here's the least amount of significant figures. That is what the answer will have as well. But here the answer will be determined by the measurement in the calculation that has the least amount of decimal places. Okay? And your answer will have the same amount of decimal places as that number. So, for instance, here I'm adding up three numbers, 10.12, 3.8, and 5.011. This one has two figures behind the decimal point. This one has 1, and this one has 3. Okay? If you put it into a calculator, the calculator will say that's 18.931. But not all of these numbers are significant. It is an addition here, so this rule applies, and it says that this answer should have the same amount of digits behind the decimal point at the least precise way. And that's this guy. Okay, so this one should have 1 digit behind the decimal point. 18.9. That's the correct answer. Okay, so after you do this calculation then, you have to chop up a couple of numbers. How do you do that? You have to round it. And the rounding happens exactly as you are used to. Okay, basically it means that if the last digit, okay, is less than a 5, then the preceding digit stays the same. If it is more than 5, the preceding digit is increased by 1. If it is equal or more than 5, the preceding digit is increased by 1. And this is exactly what you're usually using already. Okay? Now, the rounding happens after completing a mathematical operation, such as adding and subtracting, or multiplication and division. You basically complete that step. If there's another step in the calculation, you can round in between. If you don't round within the mathematical operation, and we'll see examples of that. I'll point it out to you. Okay, so let's practice this a little swiftly. Here's a number for you. There's 1, 2, 3, 4, 5, 6, 7 digits at this point. And I'm asking you to round this number to one significant figure. What is that? How do you write that? How do you do that? You have to use scientific notation here. Otherwise, you will not be able to do it. 2 times 10 to the third. Right? 2 times 10 to the third. All of these numbers disappear except for the 2, because I'm rounding up to one significant figure. What happens if the question says 2 significant figures? Well, what you do then, you look at this number here, and you look at the number before. This is a 9. That means that this 0 becomes a 1. So you get 2.1 times 10 to the third. 3 significant figures. I'm going to go one more back here. One level back. Okay, so this is going to be a 1. This is going to be a 0 because this one here, 8, is higher than 5. Meaning that the number before it is going to be lifted by 1. So this here is 2.10 times 10 to the third. And then 4 significant figures have to go one back more. Look at this guy here. This is more than 5. That means this 8 is going to be lifted by 1. And the answer is 2.099. This is not going to be 100, because you just have to look at this last digit here, whether or not it's going to lift the preceding digit. That's what you have to do. Okay? Yes?
For that one, we have to use fixed notation if we're asking like even though we already have 4 in
You don't have to use cyclic notation. That's right. You don't have to do it. You can use, you can say 2099. That's fine. Yeah. It makes just for completeness. It makes it easier to work with these numbers. Okay. Let's do a couple of operations. Let's add 2 numbers and make sure the answer is given in the right amount of significant figures. So your calculator will say the answer is 14.426, but you have to determine which of these numbers are significant. Not all of them may be. That's indeed the case. This is an addition. That means I have to look at the number of decimal places. This one has 2, this one has 3. Okay, so this answer should be in 2 decimal places as well. The last number here is a 6, it's higher than 5. That means this preceding digit 2 is going to be elevated or lifted up by 1, increased by 1, and that is 43. But this is the final answer. How about this? Another addition. 2 numbers, this one has 3 decimal places, this one 2, and know the answer should have 2 decimal places. Okay? This is what the calculator says. Again, look at the last number here, 7. It's higher than 5. That means that this number is going to be increased by 1. The answer is then 152.68. Yeah. Another question? Yes.
How do you know that it's 2 decimal places again?
2 decimal places because this is the least precise measurement. There's 2 decimal places. This one is more precise. And there's 3 decimal places. The answer should be given in the same amount of decimal places as the least precise measurement. This is a subtraction. It's the same rule. Okay, so you basically punch it into your calculator. Your calculator says the answer is 8.47, and you have to determine which of these are significant. You should have only 1 decimal place. The same as this one here. Okay. Now, again, I want you to remember, this number has 3 significant figures, but only 1 decimal place. That's what matters. Okay? That means this one should also have 1 decimal place. 8.5. Okay? 8.5, this one has 3 significant figures, this one has 2. Sorry, this one has 3, and this one has 3. The answer has only 2 significant figures. So don't be bothered by this and think that this one should have 3 as well. Because that's not the rule. The rule is look only at the decimal places, not the total number of significant figures. Okay, this is a multiplication. Now we do have to look at the total number of significant figures. This one has 3, this one has 5. The answer should be in 3. Okay? The calculator says this has to be rounded up to 3 significant figures. I have to look at this number here, 7. It's more than 5. That means that this 2 is going to be increasing by 1. And the answer is 26.3. Another multiplication. 2 numbers again. This one has 4 significant figures. This one is also 4. The decimal point is in a different position. It doesn't matter for these kind of calculations. Just the total number of significant figures. The answer should be in 4 significant figures. Your calculator says this. Okay? So what I have to do, look at the last digit here. It's an 8. It means that this 8 is going to be increasing by 1. 1349 is the answer. I can rewrite this, if you wish, in scientific notation, and that is 1.349 times 10 to the third. All right, finally, division here. 2 numbers. The rules are the same as the multiplication. Okay? This one has 5, this one has 3. The answer should be in 3. So your calculator says this number is the answer. Should be rounded up to 3 significant figures. This is a 2, which means that the 4 remains the same, 11.4. All right? This is how it works. Okay. So, there will be some examples of that on the homework. And the homework will also look into the following. Dimensional analysis. Dimensional analysis has everything to do with looking at your units and changing between one unit and the next. Okay? I'll give you examples of that. This is one of the most important topics of this course, in the first half of this course. It is making conversions between units. And there's a particular way to do it. If you stick to that method, you will not make a mistake. If you stray away from it, you will run into problems. That's just how it is. Okay, so here's the situation. This is a definition of what an inch is. 1 inch is 2.54 centimeters. Okay, that's a definition. But now I want to know how many inches is 2.85. 2.85 is not the same as this number. And I'm looking at this, I guess, well, it must be higher than 1. But how much? How do I do this calculation? Very simple. But how do you do it? Okay, so what I'm going to do now, I'm going to show you what the basics are for such a conversion. Okay? The first thing I'm going to do is to divide this equation here, each side by 2.54, like this. So this is the left-hand side. I divided by 2.5 centimeters. I'm also going to divide this by 2.5 centimeters. Okay? So what happens is, if I divide this side by 2.54 centimeters, divided by itself, is 1. Okay? It's 1. So this is 1. If I divide this side by 2.54, it means it's also 1. Because the other side is 1. So in other words, I have here an interesting situation. I have here a relation between two units. 1 inch over 2.54 centimeters is a unit factor. This thing has the value 1. And that's really good. Because if something has a value 1, you can multiply it with anything without changing the value of the other thing. So let me give you an example. Okay? Here, 2.85 centimeters. If I multiply this number by 1, it doesn't change the value. But it can change the unit. This thing here I just said is 1. It says 1 inch over 2.54 centimeters. But if I do this multiplication, I see something very interesting. This centimeter here and that centimeter there is going to cross out. Okay? Meaning, this number divided by that is now in inches. The inches stays. The centimeter will cross out. So the answer is in inches now, 1.12. This is a conversion where I'm using a unit factor to convert one unit into the next. This is what the real method entails. I have a number A expressed in unit 1. Doesn't matter what kind of unit it is. I'm going to multiply that with a unit factor which is composed of a number expressed in unit 2 over unit 1. In that case, unit 1 will strike out. My answer, B, is in unit 2. Okay? This is a short way of writing what I just did here above. So what I have to do is I need to know a definition between two units. I make a unit factor where I put unit 2 on top and unit 1 at the bottom. What is unit 1? Unit 1 is the unit you want to cross out. That unit has to cross out. That unit has to appear on the bottom. It's the denominator. The unit you want to go to sits on top. Okay? Since this is 1, you can flip this too. You can put the 2.54 on top of the 1 inch. It's still 1. You want to do that, you want to make the reverse conversion. So let me show you a couple of examples. How many miles is 1 kilometer? To do this calculation, you need to know the definitions between the units, the relations between the units. Here is a table that says 1 kilometer is 1,000 meters. We know that. 1 meter is 1.094 yards. And 1 mile equals 1760 yards. These are definitions. You don't have to memorize these necessarily. Well, the first one you have to know. These guys is just a table that I'm giving to you right now for this particular question. So, how many miles is 10 kilometers? So what I'm doing is, I have a number, I like to convert the unit into a different unit. So I'm saying 10 kilometers has to be converted into a different unit. So the first thing I'm going to do is to convert kilometers into meters. And then meters into yards, and yards into miles. So I do like a stepwise conversion. It's a good exercise. If I want to convert kilometers into meters, I make a unit factor out of this relation, where meters appears on top and kilometers at the bottom. In that case, kilometer will strike out, like this. This thing is a unit factor, equals 1. So I don't change the value. A kilometer will strike out, and now my number is expressed in meters. Next, from meters to yards. Same thing. I'm going to multiply this with a unit factor where yards appears on top, meter at the bottom. Okay? Like this. Now this m will strike out. And I've converted first from kilometer to meter, then from meter to yard. Last step, from yards to miles. I'm going to put miles on top and yards at the bottom, like that. Okay? This many yards equals 1 mile. That means 1 mile over this many yards equals 1. Yards will cross out. And now my answer is expressed in miles. In other words, what I have to do, 10 times 1,000 times this number divided by that equals 6.22 miles. I can actually, oops, that sounds very, very ugly. This should be not there. Okay? So this number 10 has only one significant figure. Okay? Only one. This is a trailing 0. And there's no decimal point. It means it is not significant. This is only one significant, so this should be 6 is the answer. Okay. Another one. Same kind of deal. How many kilometers is 55 miles? We'll do the reverse calculation. Here's the same table again. First, we're going to convert miles into yards. Make a conversion factor, a unit factor, where miles is at the bottom, because I want to get rid of that, and go to yards. This is the unit factor. Then, from yards to meters, where meters appears on top, yards at the bottom, then yards will strike out. And then finally, from meters to kilometers, I use this relation here. Kilometer appears on top. It means 0.001 kilometer over 1 meter. That is the unit factor. And that means that now miles will strike out, yards will strike out, meters will strike out. My answer is going to be expressed in the unit of kilometer. Okay, so we perform this calculation. 55 times this, divided by this, and then multiplied by this number here, equals 88. Two significant figures. A calculation is complete. Okay, another exercise. Volume. A couple of relations here, definitions, and a question. How many quarts are in 43.0 liter? Do I need all these relations? I want to go from quarts to liters, or from liters to quarts. Ah, look, this middle one here already relates these two units. That's all I need. I don't have to do it stepwise in this case. So, I have a number expressed in liters. There it is, 43.0 liters. I'm constructing a unit factor out of the second line, where liters has to go as a denominator, and this one as a numerator. Okay? Because in that case, liters will strike out, and a quart is the unit that I retain. The answer is 45.6 quarts, and that is the right number of significant figures. 3, because here I have 3 as well. Okay. One more. Mass. Relations, kilogram related to pounds, and pounds related to grams. And a question. How many grams are in 0.346 pounds? I have to go from pounds to grams. Here's a relation between pounds and grams. I only need this one here. Okay, here's the number I'm starting with, 0.346 pounds. Pounds has to strike out. That means out of this relation, I synthesize a unit factor where pounds appears on the bottom. There it is. And this number here goes on top. That's grams. This will strike out. Grams is the one that survives. And consequently, I have my answer in grams. 157 grams. Let's check significant figures. This one has 3. This one has 4. This one is infinitely precise. This is never a limiting step in the calculation. So the answer should be in 3, like that. This is the right answer. Okay, another example. Convert 0.843 centigrams into pounds and express your answer in standard scientific notation. Okay, so I have to convert something that's expressed in centigrams into something expressed in pounds. I need to know relations. Okay, so I need to know definitions. What is a centigram? Well, a centigram means 10 to the minus 2 grams. So centi means 100th. Okay, so now I relate centigram to gram. Let's also relate pounds to gram. Okay? Or kilogram, it doesn't matter in this case. You can relate centigram to grams and kilograms. There's a step of 3 orders of magnitude between grams and kilograms. So 1 centigram equals 10 to the minus 5 kilograms. 1 kilogram is 2.2046 pounds. That's the definition, that's the relation between pounds and kilograms. So now I have 2 definitions that are going to help me out. I've related centigram to kilograms and pounds to kilograms, a common unit. And now I can make a conversion. Okay? So this is how it works. I start with my number in centigrams. I'm going to express that in kilograms. Okay? Using this step right here. So the number requires a 10 to the minus 5. 0.843 times 10 to the minus 5 kilograms. That is the number expressed in kilograms. Now from kilograms to pounds, using this relation right here. Kilograms has to appear on the bottom, and pounds on top in my unit factor. Okay, here it is. Pounds on top, kilogram on the bottom. Kilogram is strike out, and my answer is going to be expressed in pounds. The calculator will say this. It's a large number, and I have to check now. This one has 3 significant figures. That means the answer also should have 3. Okay, so let's do that. This is an 8. That means this 5 is going to be increasing by 1. 1.86 times 10 to the minus 5 pounds is my final answer. So for these kind of questions, what you want to do, you want to relate the units to a common unit. Centigrams to kilograms and pounds to kilograms. Then you can make a conversion. Okay, another one. How many square? This is a very nice example. So it's one step up from the last example. How many square femtometers? Femto means 10 to the minus 15. Okay, so 10 to the minus 15 meters. How many square femtometers are present in 0.731 square attometers? What is an attometer? Atto is 10 to the minus 18. 10 to the minus 18. Express your answer in standard scientific notation. This is a little bit of an oddball. You don't have to remember attometers. I just throw it in there so you know that it exists. Okay, so the interesting thing here is this is a square. This is an area. Okay? So let's look at that carefully. The definition of a femtometer is 1 times 10 to the minus 15. And the definition of an attometer is 1 times 10 to the minus 18. That's the definition of attometer. Both are now expressed in a common unit, meter. Okay? Both are expressed in a common unit now. That's the meter. So I can relate them to one another. However, I'm not dealing with femtometers and attometers. I'm dealing with femtometer square and attometer square. Okay? So let's do the following. 1 femtometer related to an attometer is the following. Is 3 orders of magnitude, right? 1 femtometer equals 1,000 attometers. That's the relation between the 2 units. If you relate them both to the same unit, you see there's a 10 to the 3 order difference between these two. 1 femtometer equals 10 to the 3rd attometers. Now this is not a square unit yet. So let's do that. Let's square this. And square this whole thing. Okay? That means that this attometer gets a square here, but this unit, this number in front also requires power to the second power. So if you execute that step, we find the following. 1 femtometer squared equals 1 times 10 to the 6th attometer squared. Okay, so the relation between a femtometer squared and an attometer squared is 6 orders of negative. So the general rule is with these kind of things, if you have the relation between two units, then the square of them follow this kind of step. You square the whole thing. Okay? You square the unit and the number before it that is included in the relation. Okay, so I want actually to express attometer squared in terms of femtometer squared. That's the inverse, so that's this. 1 attometer squared equals 10 to the minus 6 centimeter squared. Okay? I just reverted it. That's all I did. So that is good news, because now I can directly relate a certain amount of attometers into femtometers. Here it is. This is the number, 0.731 attometers squared equals that number times 10 to the minus 6. That's it. I can rewrite it a little bit because I can shift over this decimal point to the right by 1 step, which means that the answer is now the following. 7.31 times 10 to the minus 7, because I shifted over the decimal point 1 step, it becomes minus 7. Femtometer squared is the final answer. Okay? So, this is an important kind of example where we deal with square units. Don't be afraid of them. They follow exactly this procedure. You square the whole thing that is included in the relation between the two units. Okay, another one, this is the last one. How many, this is another one. This is actually a cube as opposed to a square. So it's a similar type of question. How many cubic kilometers are present in 7.59 microliters? And express your answer in standard scientific notation. All right, let's do it. First, let's look at a couple of definitions. 1 kilometer cubed. Can I relate that to another unit? Meter. Meter is a standard unit. So what I want to do is I want to relate both microliters and cubic kilometers to the unit of meter cubed. Okay, so here we go. 1 kilometer is 1,000 meters. That's the definition. A kilometer is 1,000 meters. So a kilometer cubed is 1,000 cube meter cubed. And that is 10 to the 9. 1 times 10 to the 9 meter cubed. That is 1 kilometer cubed. Expressed in meter cubed. What about this guy? Oh man, it should be a micro. Okay? 1 microliter equals 1 times 10 to the minus 6 liters. That's the definition. A micro means 10 to the minus 6. So a microliter is 10 to the minus 6 liters. But I have to relate it to meters. So what do? I know a liter is a decimeter cubed. Okay, so let's do that. 1 microliter is 1 times 10 to the minus 6 decimeter cubed. And I relate now the decimeter cubed to a meter cubed. Okay? So that is a 10 to the minus 3 difference. Okay, maybe you remember that. A decimeter cubed is 1,000 times smaller than a meter cubed. Okay? So this, I'm doing this as a quick step. The quick step here, because I remember that from last time. A decimeter cubed is 1,000 times smaller than a meter cubed. It means, in terms of meter cubed, it is 10 to the minus 9. If you don't follow this quick step, you can ask me questions after. Okay, so now both things are expressed in meter cubed. So that's good. Remember this tiny little thing here. I'm sorry for that. I don't know why that happened. I'm going to flip this over now. Okay? I can even read myself. Let's see, what did I do? Oh, here. Yeah, this here, I'm going to now write in terms of a meter cube. 1 meter cube equals this many microliters. Okay? So 1 kilometer cubed equals, here, this is the definition, 1 times 10 to the 9 meter cubed. The meter cubed is this. I just wrote that. Okay, so 1 meter cubed equals 10 times to the 9 microliter. That is meter cubed right there, expressed in microliter. I apologize for the cipher versions. I don't know what happened. This is microliter. Okay? So I expressed here kilometers in microliters. This is what I find. 1 times 10 to the 18 microliters. 1 kilometer cubed is 1 times 10 to the 18 microliters. If you upload the slides on the website, I promise that the science will be correct. This is a Mac to PC conversion problem. This thing should not be there. This is a micro sign, okay? A mu. Okay, so if I invert that, 1 microliter, in terms of kilometers, 1 microliter equals 10 to the minus 18 kilometer cubed. Okay? So I've related kilometer cubed to a microliter. 1 microliter equals 10 to the minus 18 kilometer cubed. The trick to get there is to relate both to meter cubed, and then write one in terms of the other one. Okay, so now I'm very close to the answer. This is given in microliters, 7.59 microliters. 1 microliter is this. So I just have to substitute this unit for this, and I have the answer. Okay, the answer is 7.59 times 10 to the minus 18 kilometer cubed. Okay, thank you, folks. I'll see you on Monday.